What a sight. NASA's Mega Moon rocket is on the launch pad after recently completing a wet dress rehearsal here in Florida. It is not launching today, but before a rocket like this one starts launching missions to help assemble a space station in orbit around the moon, NASA is first enabling a small CubeSat called CAPSTONE to test out that same lunar orbit. And we're taking you live to New Zealand for that Rocket Lab launch next.
I can hear the demons call when they do what they do. And now I feel like taking off, find a place with a view. The pain is never gonna stop if it's controlling you. I know that time can heal it all, I just gotta get through. I just gotta get through, I just gotta get through. Cause I feel like taking off, find a place with a view. The pain is never gonna stop if it's controlling you.
Off from Launch Complex 1 on the Mahi Peninsula in New Zealand. It's dark out there, just a few hours after sunset for our friends in New Zealand, which time-wise, right after 9 p.m. local time. Liftoff is 9:55 p.m. local time. That's 5:55 p.m. Eastern time. And if all goes well, that Electron rocket that you see on the pad there will light up the night sky carrying NASA's CAPSTONE spacecraft towards the moon. Back here in Florida, thank you for joining us for live coverage of the CAPSTONE launch. I'm Daryl Nail, and as I mentioned earlier, that's NASA's moon rocket on the pad behind me with the Orion spacecraft. It's on Launch Complex 39B, and preparations are being made to roll that SLS rocket back to the vehicle assembly building on a gigantic mobile crawler currently scheduled for Friday. But when the launcher and moon rocket return to this pad, they will be ready for Artemis 1, an uncrewed test flight on an orbit around the moon. That has yet to be scheduled. But now, back to today's mission. Before Orion goes to the moon, we're sending CAPSTONE first, a satellite the size of about a microwave oven, which will demonstrate a new way to guide a spacecraft around the moon without relying on Earth-based communication. CAPSTONE stands for Cislunar Autonomous Positioning System Technology Operations and Navigation Experiment. It's a mouthful, and here are some fast facts about it. It's a 12-unit CubeSat, and as you can see from this animation, it has solar arrays and thrusters, small ones, at the bottom. The dimensions without the arrays are just 1 by 1 by 2 feet, or 34 by 34 by 61 centimeters. And it weighs just 55 pounds or 25 kilograms. And it doesn't need much of a push from its monopropellant hydrazine system because this orbit it's going into is very efficient. The mission is funded by the Space Technology Mission Directorate, which develops transformative space technologies to enable future missions. But first, let's get an update on preparations to launch CAPSTONE on an Electron rocket by taking you literally halfway around the world to Rocket Lab's Mission Control Center in Auckland, New Zealand. That's where launch commentator Muriel Baker is standing by. Muriel, we're separated by 8,000 miles, so there's a little bit of a delay between us. It's not nearly as long as the time difference, though. 16 hours, you're ahead of us here on the eastern coast of the United States. But I say to you, good evening, and for us, good morning.
Thanks, Daryl. That's right. Welcome to quite literally the future of space exploration. It is just at T-minus 51 minutes to the countdown, and here in New Zealand, I'm joining you live from the Rocket Lab Mission Control Center in Auckland to take you through today's launch of the CAPSTONE mission from our country's eastern shore of the North Island. Our Rocket Lab launch operators are making their way through the count with checks on the systems and the health of the Rocket Lab Electron launch vehicle and Photon lunar upper stage, as well as the CAPSTONE spacecraft integrated to Photon. All three are sitting on the pad at Rocket Lab Launch Complex 1, as you can see there, on the Mahi Peninsula, from where we will launch the Electron rocket on an eastern trajectory over the South Pacific Ocean. Now, liftoff is currently scheduled for 21:55 local New Zealand time, or 09:55 UTC. In Eastern Daylight Time, that translates to 5:55 in the morning for you, Daryl. Sorry about that. And for Pacific Daylight Time, liftoff is scheduled to a even unfriendlier 2:55 a.m. Our latest status update from our weather official in Mission Control reported clear skies over the launch site. The weather is nice and still this evening, with the probability of violation very low, meaning we are very close to that launch liftoff. Now, over the past few hours, Rocket Lab's launch crew on the ground and in mission and range controls have been readying the launch pad with vertical and avionics checks with the rocket, and have loaded Electron with its propellant types, kerosene and liquid oxygen. So right now, with just about 50 minutes left to lift off, all systems are go for launch, and I'm going to hand it back over to you at Kennedy, Daryl.
All right, great report, Muriel. And quick question for you. Why launch from New Zealand?
Daryl, if you're looking for a launch site anywhere in the world, the ideal location is an island in the middle of the ocean, which New Zealand as a country makes a great option for. And if you're going to launch east, which you would like to do because you get that free push in the same rotation of the Earth, then the east coast of New Zealand is a great place to be, and Mahia on its peninsula jutting out over into the coast is a wonderful spot because we have very little air and marine traffic. So it's really a one in a million location.
It certainly is, and it's incredibly gorgeous, especially during the daytime. And hopefully in the future we can show you a daytime launch as well. Well, we've got a lot of cool stuff to show you coming up in our pre-launch show, as well as some great interviews. First, we'll take a closer look at the CAPSTONE mission itself, the very first spacecraft to fly as part of the Artemis program. Plus, we'll speak to an expert about this, the rectilinear halo orbit. What do we expect to learn, and how will we use the data? And from CAPSTONE to Gateway, we'll talk to a NASA expert about the latest on plans for a lunar outpost where NASA astronauts will dock before going down to the surface of the moon. After liftoff, it will take about 4 months for CAPSTONE to get into the near rectilinear halo orbit. Here's more on the orbit and the CubeSat 6-month Pathfinder mission for the Lunar Gateway.
Before NASA's Artemis astronauts go to the moon, a small spacecraft called CAPSTONE will help lead the way. The Cislunar Autonomous Positioning System, Technology Operations and Navigation Experiment will test a unique lunar orbit that has never been flown before. This orbit will be home for NASA's Gateway, the future space outpost that will support visiting astronauts on their way to the moon and beyond. To help prepare for Gateway operations in this orbit, CAPSTONE will fly the path first. The mission will be led by small business partner Advanced Space. Rocket Lab will launch the spacecraft. The gravities of Earth, the Sun, and the Moon will help propel it into deep space. As it nears its destination, CAPSTONE will use its propulsion system to enter an elongated path around the Moon. The spacecraft will orbit between the gravities of Earth and the Moon in a precisely balanced dance. For 6 months, it will gather data about this crown-shaped trajectory known as a near-rectilinear halo orbit. The path provides an unobstructed view of Earth as it orbits the Moon's poles, and allows for continuous communications with ground-based control centers. CAPSTONE will also demonstrate a new onboard navigation system. It will communicate with NASA's moon-observing Lunar Reconnaissance Orbiter satellite to calculate its position. The technology could allow future spacecraft to pinpoint their location without having to entirely rely on tracking from Earth. CAPSTONE's flight will demonstrate how this unique lunar orbit can support future spacecraft around the moon, helping to launch a new era of human space exploration.
Joining us now is Dr. Jeff Parker, the Chief Technology Officer with Advanced Space, the company operating this mission for NASA, and he brings CAPSTONE, a literal life-size model of the exact spacecraft. What's great about this is you get perspective of how big this spacecraft is. It's this big.
That's right. This is a 12U form factor satellite. It's a full spacecraft in a small body. It's got a propulsion system down here. It's got an antenna that talks to the ground here. This is the antenna that talks to the Lunar Reconnaissance Orbiter, another satellite in orbit about the moon. Solar panels. These extend, so this isn't a fully unfurled solar panel, but yeah, that's right.
It's about right. The microwave oven was the analogy given, and it certainly looks like it's exactly that. Tell me, this is going into this near rectilinear halo orbit. How will it do that, and what's it going to do when it's there?
You bet. So the near rectilinear halo orbit is a challenging orbit to say, but it's a really impressive orbit for its operations. We use a low energy transfer to get this guy into that orbit, and it uses very little fuel to get there. When we get there, this is a model of what the orbit looks like. Hopefully we can see that.
Yeah.
So Earth is in the middle, Moon goes around, and we form this crown shape about the Earth there. And then this orbit is just fantastic for what it needs to demonstrate. There we go. And it takes very little fuel to get into this orbit using this certain type of transfer to get there. And then it takes very little fuel to get down to the surface of the moon. We might even be able to use it to go out to asteroids. It's a gateway, and we're demonstrating this as the gateway for the Artemis program.
We're seeing a beautiful shot of Capstone right there on the top of the Electron rocket. You're with Advanced Space. We've got that team as well that's online tonight. They'll really start working when the mission fires up. What challenges do you expect to find once this gets into its orbit?
So nobody has ever flown one of these orbits before. Now, we have demonstrated this in simulation many times. We're ready for anything, even contingencies, but spaceflight is challenging. So we're ready for anything. We're going to go head on and teach NASA every lesson we learn.
And there's your team waving at us live from Colorado. That's the Advanced Space headquarters in Colorado, where Capstone Mission Operations Center is located. A lively bunch tonight. Again, they're going to get working in 6 days.
That's right. That's right. I love this launch. It gives us 6 days to prepare between launch and the time that our team picks up the satellite on the way to the moon.
So tell me, what other lunar orbits were considered when you were first developing this? Because, NASA gave you the funding for this mission and then said, hey, check it out for us.
Oh, sure. Yeah, we looked at a lot of different orbits like this, and they all had to have the same kind of requirements. So they all had to have a low fuel requirement to get this satellite, which only has so much fuel, into that orbit. Has to be a gateway, just like NASA's doing. And then NASA in general has tested out a lot of different orbits. We've landed on this NRHO because of its terrific viability.
And with this spacecraft here, when it maneuvers, it's these small little jets here at the bottom. Is that right?
Yep, that's right. Yeah, it has enough fuel to do everything we need. We have enough fuel for an extended mission as well. It's a monopropellant hydrazine system. Yeah, full spacecraft.
And so in order for it to know where it is, are you telling me this antenna up here is what communicates with the LRO?
Yeah,
another spacecraft.
That's right. Our spacecraft has two radios, one to talk to the Earth, which is a conventional approach, and one to talk to another spacecraft, the LRO. And this is a reverse radio for LRO, so it's perfect to talk to LRO. We're going to demonstrate navigation in a couple of ways. One with communications with LRO, which should be enough to navigate the spacecraft. Another one to do one-way communications with the DSN, which is a future advanced navigation technology. Everything we can do to try to help enable future lunar exploration. We envision a future that has a lot of missions in orbit about the moon. We're trying to help that out.
Absolutely. Thank you for bringing this. This is great, and for describing it, Jeff. But now we're going to go to the real Capstone you see on your screen there and check back in with the launch team and our commentator, Muriel Baker. How are we looking so far, Muriel?
Thanks, Daryl. On your screen right now is the Range Control Center, located just a couple of kilometers back from the launch pad itself on the Mahia Peninsula. This peninsula is culturally significant to local Māori people with ancestral ties to the land, so I want to acknowledge first the mana whenua, or the local people, for today's historic launch. Now, within range control, along the back row of the control center, starting from the right of your screen and moving left, sits two of our photon engineers making the spacecraft's tank managing the spacecraft's tank and communications, and our IT support engineer. Across the aisle is our senior launch conductor supporting the flight director based out of Mission Control in Auckland. Next to them are two engineers responsible for the health of the Electron rocket's engines and its reaction control systems. Their call names are Prop and Stage. So in front of them sit the engineers looking after Electron's guidance, navigation and control, and monitoring the state of the rocket's flight computers and software. Along the front row sits our GCs, or ground control operators, who monitor the launch pad's ground systems. And to their left, on the right of your screen, closest to the camera, are the avionics operators with eyes on the operational status of the rocket's electrical systems. Behind them in the middle are the range and launch safety officers, keeping a close watch on the launch pad's surroundings. Now, cutting to Mission Control here on your screen, this hub is in Auckland, and it's home to our engineers and technicians whose focus is on our Photon and Lunar upper stage and the CAPSTONE mission beyond Earth orbit. In the front row, furthest from the camera starting from the right, we have engineering support for the flight software on the Photon Lunar upper stage. In the middle of the row to the end are the engineers managing ground tracking for today's launch. And then on the end is our operator with eyes on Photon's Hypercurie engine. Behind them, starting closest to the camera and moving right, we have the guidance, navigation and control engineers who are across Photon and CAPSTONE's path to the moon. Their call name is Fido. In the middle sits the spacecraft engineer supporting Photon's communication software, and on the end sits Space Ops software ensuring our telemetry makes it from the Photon spacecraft to the operator. Now moving to the back row, starting from the right, sits our weather officer for today's mission, followed by the engineer managing the IT systems, linking range and mission controls, and then our team lead, responsible for our hardware simulation platform called HITL, which we use to simulate multiple flights to orbit before each mission we launch. And next to them sits Tank, which monitors Photon's fluid systems to ensure its Hypercurie engine is provided with its propellants. And finally, at the end of the row is our Director of GNC, Dr. Jonathan Curry. So with that, we are now at T-minus 38 minutes and counting, and proceeding comfortably with the countdown to liftoff. A quick reminder that launch today is set for 9:55 p.m. New Zealand time, or 9:55 a.m. UTC. Over to you, Daryl.
All right, thank you, Muriel. And it'll be 5:55 a.m. Eastern time as well. Joining me now is Ali Guarneros Luna, project manager for NASA's Small Satellite Program. She's here to talk about why CubeSats like CAPSTONE are proof that small satellites can have a big impact. Thanks for being here.
No, thank you for having me today.
So why would NASA choose a small satellite instead of a large one?
Well, I mean, the reason why we choose small satellites is to be able to understand the risk of the missions that we're trying to develop, and small satellites actually gives us the benefit of doing, taking bigger risk. And so having the small satellites being able to, utilize and develop the technology for the bigger missions like the Gateway, is one of the reasons why we choose the CAPSTONE.
And so what are the most important factors when you go to design a small satellite?
Well, definitely, I think it's going to be understanding the mission architecture, where you're going, understanding the requirements, the environment, and, trying to develop that technology so you can infuse it later into the bigger missions.
It's fascinating to hear about how NASA is working with small businesses and these small satellites to get big jobs done. What are the biggest technological advancements you've seen in small satellites?
I think the beauty for small satellites has been that not only are we able to develop the technology really fast and quickly, and mature it, but also being able to now do a pathfinder's missions like the CAPSTONE is going to be for the Gateway. And so that actually gives us a lot of benefits because we can turn around and really develop that and mature that technology.
Which will help the mission behind us right here, which is the SLS not launching today, but a beautiful shot on the pad. We've got two different rockets on two different pads in vastly different locations. On a more personal note, Ali, I was reading an article about your personal journey here, and it begins with an 8.0 magnitude earthquake in Mexico City back in 1985. 5,000 people killed. Devastated Mexico City, where you were born and raised. before you came here. Tell me a little about your personal journey and how that sparked you and your mother's journey here to the United States.
Well, definitely. I mean, it's a long story, but just to make it short, when the earthquake happened, my mother, had 4 children. I was the oldest one of 4, and she did not really had a well education. So for her to be able to survive, in Mexico at that time, it was not viable. So she decided to move to the United States and, move with her 4 children. And I was, the oldest one. So I moved with my mother here, and, I had to learn the culture, understand, learn the language too, right? And then be able to get adjusted to this new world. And, it took me some time, obviously, like anybody,
You went to school,
yes,
dropped out because of it, and then went back.
That's right. I decided to go back to school after many years because, I have 2 small children with mental illness. And for me, that was the drive to actually, get into school and get a degree, to be able to have them, to have a better life. And for me, going back to school was the drive. And so I did it, and I graduated. And then when I was graduated, my professor actually told me there's an internship at NASA. I ended up, working at NASA, not thinking that that was the path that I was going to take. But, I'm here, and I'm really happy to be here.
How about that? What an inspiring story, Ali. Thank you for sharing it with us, overcoming all those hardships to be here at NASA.
Thank you.
Good luck on the launch, and thank you again for being here. Well, we've showed you how Capstone is a pathfinder mission for NASA's Lunar Gateway. As NASA astronaut Randy Bresnik will show you, the planned orbiting lunar outpost is the first step to fulfilling plans for a more permanent presence on the moon.
Home. For me, home is where my family is. But there have been times in my life where I was called away from my family for extended periods of time. While I was serving in the Marine Corps, it was hard to be away from my loved ones. But thankfully, I had my squadron family, but other places where we were stationed around the globe became a temporary home. Then, in 2009, I launched the International Space Station, traveling even farther away from my family, conducting science 250 miles above the Earth. The space station was an orbiting home for my crewmates and myself. Talk about a room with a breathtaking view. With Artemis, NASA will send the first woman and the first person of color to the moon. We are going there for the benefit of all here. We'll need a place to orbit around the moon, where we can live and work, a place to get ready for our lunar surface expeditions, and a place to return to when our work on the lunar surface is complete. We need a lunar home away from home. This will be the Gateway. Starting with the power and habitation modules, the Gateway will be the first long-term outpost in lunar orbit humans have ever had. Primed for new discoveries, this orbiting laboratory will provide us with a unique view of our solar system. And it's already becoming a beacon for the future of international and commercial cooperation in space. With increasing capability and longer missions over time, the Gateway will be a powerhouse of technology and science, paving the way for future human missions to Mars. Design and fabrication of Gateway elements by NASA and our international partners is well underway around the world right now. Wherever you are on planet Earth, today you are part of the Artemis generation. I'm NASA astronaut Randy Bresnik, and I invite you to join us by following NASA Gateway on social media and telling us where you call home.
T-minus 31 minutes and counting until launch in New Zealand with our NASA Mega Moon rocket here on the ground as a backdrop. It's time now to dive into the details of Capstone's orbit, the near rectilinear halo orbit. I spoke to Najude Moranci, chief of the NASA Exploration Mission Planning Office, about it. Najude Moranci, thank you for being here. We're launching, of course, Capstone today, a microwave-sized CubeSat that's going into this near rectilinear halo orbit. Eventually, it will lead the way for Gateway, a much larger lunar outpost where astronauts will go. What's the difference between getting Capstone into that orbit versus the Lunar Gateway?
One of the really interesting things with the orbit mechanics is we can sort of play with, how much propellant it takes to get somewhere and the time it takes. So CAPSTONE is using a ballistic lunar transfer. So it'll take 3 months to get to NRHO, but it'll use a quarter of the delta velocity that we'll need when we fly this with Artemis and the crew. So the crew will only spend, 5 to 10 days in transit. We'll fly very close to the moon and use the moon to slingshot us out there, but it takes more delta velocity or, relative propellant amount. So, we can play with both the time and the duration to get into NRHO based on whether we're flying crew or you're doing something so uncrewed like the CAPSTONE mission.
And looking at this near rectilinear halo orbit, you can see it really goes quickly around the moon, but spends more time away from it. Why is that, and are there advantages or disadvantages to that?
Yeah, so the NRHO, or near rectilinear halo orbit, it's an elliptical orbit. So when you're close to the moon, the spacecraft, any spacecraft will fly very fast. You'll go over the north pole of the moon in about a day, but then we spend about 6 days over the big part below the south pole of the orbit. So you go very fast close to the moon, slow when you're away from the moon. But the reason we're in this orbit is it's incredibly stable, but also relatively close to the moon. So with that stability, we only need the equivalent of 10 meters per second of delta velocity for a whole year to maintain the orbit, which is very small in spacecraft terms. So that means we can put the Gateway there for 10, 15 years and not need a lot of propellant to keep it there. But it's also close enough to the moon that the human landing system can access the South Pole. We can do the human exploration in the future, as well as have that stability for a good outpost capability. So really it was that balanced orbit for the long-term planning of Artemis and the objectives we need for human exploration.
Oh, that's very interesting. And so what is required in order to maintain that very unique orbit? Is it difficult?
So the orbit should be relatively easy to maintain, but that's why we want CAPSTONE to go first so we can collect all the data and validate the models. So it doesn't really matter what size the vehicles are, the orbit mechanics will work the same. So with CAPSTONE as the sort of pathfinder, it can demonstrate the navigation, the guidance, the propulsive capability to maintain the orbit, and we can really just extract from that the math to validate the orbits for Gateway, Orion, and Artemis missions. So the maintenance of the orbit is really fascinating, easy thing to do, so we can use these two missions to compare how they work. But the other advantages of this orbit is it's very stable for power and thermal and has continuous communication with Earth. So, the operations in this orbit are really good for that long-term deep space exploration capabilities that we want to demonstrate.
Najib Moranci, thank you so much for your time today.
Thank you for having me.
CAPSTONE packs a lot of technology into a very small package, and that's thanks to the engineers behind the spacecraft.
We're incredibly excited to be leading the CAPSTONE mission for NASA and demonstrating critical technologies that will not just help people return to the moon, but will help people stay at the moon.
Before NASA sends their human-rated spacecraft, we want to send our CubeSat CAPSTONE to kind of work out the issues of how do you operate in this type of orbit? How do you do station keeping? How do you do navigation?
CAPSTONE is a pathfinder mission. CAPSTONE is going to be demonstrating how to put a space station at the moon.
So it's important for us to characterize that orbit and to understand what it is like to have spacecraft in that orbit.
The CAPSTONE mission is important because we'll be one of the first to explore the NRHO, the near rectilinear halo orbit, in and around cislunar space, which will provide valuable experience and knowledge for NASA when they operate their Artemis missions.
What I think makes it a really interesting orbit is that it's kind of like balancing a pencil or a pin on the tip. Like, theoretically you can, but you never actually can.
At its core, CAPS is a peer-to-peer navigation system.
So CAPS is the Cislunar autonomous positioning system, and we'll be using that to sort of do autonomous lunar navigation in addition to demonstrating the near rectilinear halo orbit for NASA.
CAPS enables a future where many spacecraft can talk to each other, and they can help each other navigate, figure out where they are, avoid collisions, carry out their objectives, and so on.
Instead of talking to the ground, we can talk just directly with LRO and determine where we are in space, determine our position and our velocity in space.
You don't just know that you are, X kilometers separated. You can actually estimate the full 6-dimensional state of both of those spacecraft. People have shown that mathematically for probably 15 years at this point, and this will be the first time that we actually get to demonstrate it in space.
Going to the moon is about learning. It's about learning how to operate in deep space without a lot of support from the ground.
I think it's very cool that we're working to put people back on the moon, especially because when I was growing up, that wasn't a big thing. It was a big thing we had done, but not a big thing that we were doing. And so I think it's really cool to be part of the generation that's kind of bringing that back.
Space travel is kind of like sea travel was many hundreds of years ago. It's hard, it's dangerous, but the resources out there, the knowledge out there will have tremendous impact on human life in the future.
It has been an exhilarating 2.5 years leading the development of the CAPSTONE mission for NASA. But what I'm most excited about is this is just the beginning of developing a foundation for the permanent return of humanity to the moon and a starting point for us to explore the rest of the solar system.
Well, you heard from the Advanced Space engineers. Now you're seeing them live. This is Advanced Space headquarters in Colorado, where the CAPSTONE Mission Operations Control Center is. They will jump into action 6 days from today. That's when the spacecraft separates. The Advanced Space team will then assess CAPSTONE's orbit, operate the payloads, and communicate with CAPSTONE through NASA's Deep Space Network and Terran Orbital. Back out to the pad, T-minus 24 minutes and counting. Here's a quick overview now of the launch preparations and what we can expect in the final minutes of countdown.
The countdown to launch is the most closely watched clock in mission control. Here are some of the things that take place at each milestone after the countdown begins. At T-minus 9 hours before launch, our crew are on site at Launch Complex 1 to configure the pad for launch and prepare to power on Electron for the day's operations. Meanwhile, our operators in mission control start checking in to their stations. At T-minus 7 hours, our operators will brief the launch director with a status update. Mission Control also receives its first weather check on what to expect at liftoff, including cloud cover and predicted wind speed at Launch Complex 1. Now, at T-minus 6 hours, our ground tracking stations begin to power up before Electron is prepared to go vertical on the pad. Soon afterward, Electron's Rutherford engines are tested with a short burst of engine fire to confirm all systems are operating as they should. At T-minus 5 hours through T-minus 3 hours, our range safety team runs through safety status checks for those on and around our launch complex on the peninsula, making sure the team and the public are kept safe during the day's launch attempt. Fuel loading of kerosene will soon begin on Electron, while additional vertical systems checks take place and the pad is evacuated. It's T-minus 3 hours now, and soon liquid oxygen will begin to flow into Electron. As the rocket slowly fills with this oxidizer, Electron's black body turns white as humidity in the air around the rocket freezes into a thin sheet of ice due to the freezing temperatures of the liquid oxygen inside. With 1 hour left to launch, it's crunch time for our operators. Vehicle cameras are switched to their launch settings. Our avionics team enables Electron for flight. Our final weather brief comes through, and the range safety status will confirm that the area is clear for launch. With 12 minutes left in the count, our launch director runs the go, no-go poll with our operators to make the final decision to proceed with the launch. All final checks are completed before we reach T-minus 2 minutes in the countdown. At this critical point, the countdown auto sequence begins and Electron's flight computers take over. The launch director begins counting down to liftoff from T-minus 10 seconds before the engines ignite 3 seconds before launch, and Electron lifts off the pad at T0 on its way to complete its next mission with the satellites on board.
And I was made aware of one more small launch preparation, and that is eating the good luck peanuts. Dr. Jeffrey Parker is here. He's had his, and it's a tradition of navigators to do so before a big mission. Well, CAPSTONE is flying on a small rocket, but it has a long journey to get to the moon. A key technology that will get CAPSTONE there is the third stage of the Electron rocket called Photon. Let's head back down to New Zealand and join Muriel for more on that. Muriel?
Thank you, Daryl. So to get the spacecraft out of low Earth orbit and on a ballistic lunar transfer to the moon, for the first time Rocket Lab is using its lunar configuration of our Photon spacecraft bus. Now, unlike the Apollo lunar missions of the 1960s and 70s, which took a free return trajectory to the moon, a fuel-efficient ballistic lunar transfer makes it possible to deploy CAPSTONE on a distant orbit using a small launch vehicle. The first 9 minutes or so of the mission will follow the typical mission profile of an Electron launch. The rocket will complete liftoff, first and second stage separation, and finally end with Photon separating from Electron's second stage in an elliptical orbit. Now that is where things start to get interesting, because once separated from Electron, Photon will carry out a series of orbit-raising maneuvers using its hypercurie engine, stretching its orbit into a prominent ellipse around Earth. About 6 days after launch, a final burn from the hypercurie engine will accelerate Photon to 24,500 miles per hour, enabling it to escape low Earth orbit and set CAPSTONE on a course for the moon. Within 20 minutes of the final burn, Photon will release CAPSTONE into space for the first leg of the CubeSat solo flight, and then CAPSTONE's journey to NRHO is expected to take around 4 months from that point. Now, once successfully inserted into the orbit, CAPSTONE is expected to remain there for at least 6 months, allowing NASA to study the orbit's dynamics. Now, here are two pivotal members of our Photon team to explain more about our Photon lunar upper stage.
My name is Hassan Mosley. I'm the Chief Engineer for Space Systems at Rocket Lab.
I'm Rich Hunter, and I'm a Mission Design Engineer on the GNC team.
My job is to oversee the entire technical progress of the mission between conception to delivery of the 12U CubeSat to its end destination.
I do mission design and flight dynamics for CAPSTONE, and I combine all that into a picture of what Photon and Electron are, and use that to design and optimize trajectories to get us from LC1 to putting CAPSTONE on a ballistic lunar transfer to the moon.
It's the most unique mission I've worked on at Rocket Lab so far. We've taken our Electron kick stage and turned that into a full functioning spacecraft, added a lot of delta V to its capability in order to be able to deliver the CAPSTONE vehicle into this higher energy orbit.
Traditionally what they did is they'd line it up right and they'd burn in one direction for a very long time to get the energy they needed to basically put them on a translunar injection or a translunar orbit. That is less efficient if you have a lower thrust engine. The way to get around that is to simply split that burn into multiple burns over the course of several orbits. So rather than build your orbit from circular to a translunar injection in one go, you build it from circular through a series of successively more eccentric orbits through a number of burns. So rather than one, like Apollo, we're doing 8 burns to build up our translunar injection. And the cool part about the initial phase of the mission, even though it's on day 1 of 6, is the T0 that we launch into will set our right ascension, one of the orbital elements that defines our orbital alignment. And as soon as we launch into that orbital plane, our right ascension at our payload deployment 6 days into the mission is set. And then 10 minutes later, we'll do our first hypercurie maneuver, which will set the line of apsides, which is another measure of orbital alignment. So then 2 of the alignment parameters are set within the first 20 minutes of the mission. So we need to set them really accurately so that they'll drift onto a moving target, to then hit a moving target, which is the moon, kind of 3 months later. When the mission ends for everybody else, I expect we'll be trying some zero pressure, deep space maneuvering to test our comm systems and our propulsion system and our Cislunar navigation for other missions like Venus.
I'm really proud of the technology we developed for this mission, but I'm most proud of the fact that this technology extends to future missions for Rocket Lab and NASA, such as our Mars Escapade mission.
We are coming up soon on the go, no-go poll, one of the final gates we need to pass through for Electron and CAPSTONE to leave the pad for today's mission to the moon. Our talented and dedicated team have been making their way methodically through launch pad, range, and vehicle preparations in the hours before liftoff. So to confirm we are proceeding all the way through to launch, let's listen in to mission control for that final go, no-go pull. That will be coming up in just a few moments, and we'll keep our fingers crossed for some very good news there.
All right, all stations LD on mission, proceeding with the go, no go poll at this time. Stage, there you go.
Stages go.
Avionics.
Avionics is go.
GNC.
GNC is go.
VMS.
VMS is go.
T1.
T1 is go.
GC.
GC is go.
PLS.
PLS is go.
RSO.
RSO is go.
MET.
MET is go.
MM.
MM is go.
Tank.
Tank is go.
Prop Charlie.
Prop Charlie is go.
AV Charlie.
AV Charlie is go.
Ecom.
Ecom is go.
C2.
C2 is go.
Fighter.
Fighter is go.
LD sub.
LD sub is go.
On all stations, that is the go, no go sequence complete. We're currently T-minus 14 minutes, 8 seconds and counting. We'll go for terminal count start at T-minus 10 minutes. Be advised from this time the 3-word procedure is in effect.
And there we go. That is a clear run through status checks. And as you heard, we are moving forward to the launch of the CAPSTONE mission to the moon. Our T0 launch time remains 9:55 p.m. New Zealand local time and 9:55 a.m. UTC, or 5:55 a.m. and 2:55 a.m. Eastern and Pacific. So let's go back to the Kennedy Space Center in Florida, where Daryl is with another special guest.
Thank you, Muriel. Got all the times covered. Appreciate that. Joining us now is Justin Treptow, Deputy of the Flight Opportunities and Small Spacecraft Technology Programs, to talk about how small businesses played a large role in this mission. Justin, great to have you back. You used to work here, spent 10 years here.
Yep.
You're now up at headquarters, but back in Florida for this launch.
Absolutely. I'm extraordinarily excited to be here for our lunar mission.
First question, why does NASA partner with small businesses like the ones that were involved in the CAPSTONE mission?
Well, it's an interesting interplay between government and commercial companies. With spacecraft getting smaller and more capable, we're seeing more entrants getting into the space industry. And as they get more and more experience on orbit, they're demonstrating real capabilities that NASA can partner with to lead missions like CAPSTONE and really take a leading role in gathering data that we can use for other projects. This spools into the ability to have those companies turn those capabilities into services that you can buy as another government organization or other parts of NASA. We heard an interview with Rocket Lab earlier talking about their Escapade mission. Mm-hmm. They developed the lunar photon, which is being used for another NASA mission, which would not have come to pass if it wasn't for the CAPSTONE mission. We wouldn't have the data for Gateway to take advantage of if Advanced Space wasn't here as a commercial partner on this project to bring the data from one project to another project.
That's fascinating. So you mentioned some of the benefits already that have been gained. And we've seen that through the development of CAPSTONE, right? Because NASA says, hey, go develop this. And then if there's spin-offs that are beneficial in other areas. You're starting to already see that with Capstone?
Yeah, absolutely. Some of the examples, like one of the most obvious ones, is with the Capstone propulsion system itself. Having a high delta V propulsion system on a CubeSat form factor is something that is, in the small sat world, kind of the holy grail. Being able to go somewhere and actually do something of value is really useful. And having Stellar Exploration develop a propulsion system that Capstone's using to get into orbit around the moon in the NRHO and to stay there for an extended period of time is a propulsion system that's showing up in other commercial products that's infusing within the industry. So we're seeing the technology that NASA's funding for our missions go into other places within the space industry.
Already, so quickly, early on in this. That's impressive. We're now T-minus 10 minutes and counting until the liftoff of Rocket Lab's Electron rocket. I want to ask you about a previous Rocket Lab mission that NASA did. You're familiar with it, Alana 19, as part of the Venture Class Launch Services Initiative. What was the benefit of that, and what did we learn from that we're moving into this mission?
So the initial Alana 19 flight was a Venture Class Launch Service. Rocket Lab was a very new entry to the launch market at that point, and NASA wanted to get an opportunity to work with them on a project. And what we learned from that is that companies like Rocket Lab, like Tyvak, the bus supplier for this mission, they're very capable bringing their commercial best practices to the table and are able to really lead missions and projects. So it has, Alana 19 and the Venture Class Launch Service was like this first stepping stone to getting into these more advanced missions where our industry partners, again, are really taking a strong lead in the overall mission.
And briefly, Justin, give me a sneak peek at what's coming down the line. Any exciting partnerships with small businesses similar to this Capstone mission?
Yeah, so in the near future, we have a number of other CubeSats that are in the work. They're also going to be doing big technology demonstrations in small packages. We have Lunar Photon also going to the moon to shine a laser into the permanently shadowed craters of the moon to look for water. We have a Starling constellation of small spacecraft that is going to be doing on-orbit networking demonstrations and interfacing with other commercial partners on orbit, helping to alleviate conjunctions and to make space easier to access for all participants.
Justin Treptow, thank you very much, and welcome back.
Thank you very much, Joe.
A quick programming note before we go back down to New Zealand. I want to let you know that later this morning, Northrop Grumman's Cygnus spacecraft will be departing the International Space Station at 7:05 a.m. Eastern Time. We will have live coverage here on NASA TV starting at 6:45 a.m. Eastern Time. Again, Northrop Grumman's Cygnus spacecraft will be departing the International Space Station at 7:05 a.m. Eastern Time. All right, let's head back down to New Zealand. We are T-minus 8 minutes and counting, and Muriel Baker with the countdown.
Thank you, Daryl. It is T-minus 8 minutes and 10 seconds until liftoff. If you're just joining us, welcome to Rocket Lab's Mission Control Center in Auckland, New Zealand. Things are looking great so far for an on-time launch today from our private orbital range, Rocket Lab Launch Complex 1 on New Zealand's eastern shore. Now, you have seen the launch range and inside our mission and control centers. Now it is time to get you acquainted with the Electron rocket lifting off the pad today. And as you will have seen earlier in the show, we are taking an unconventional path to the moon, and that is because Electron is an unconventional rocket, the first of its kind in many ways, and one of the smallest orbital rockets in history to attempt to launch a spacecraft to lunar orbit. So here's a little bit more on Electron.
A small launcher dedicated for small satellites, Electron was the first of its kind to reach orbit when it first took to the skies in 2017, opening up access to space for small satellite operators. Today, it is the second most frequently launched U.S. rocket annually. More than 140 satellites have found their home in space across more than 24 Electron missions launched from Rocket Lab Launch Complex 1, the world's first and only private orbital spaceport. Designed, manufactured, and launched by Rocket Lab, Electron is a two-stage launch vehicle powered by liquid oxygen and rocket-grade kerosene. Much of its structures are made of advanced carbon composite material, including its propellant tanks, which is what gives Electron its sleek black look. The rocket is powered by 10 Rutherford engines, 9 at the bottom of the first stage, and a 10th space-optimized engine to power the second stage to orbit. The Rutherford engine is the world's first to use an electric pump feed cycle for orbital space travel, making use of electric motors and batteries to drive its propellant pumps. It's also 3D printed using additive manufacturing processes. Electron is also equipped with a third upper stage that serves as in-space propulsion to deploy payloads to orbit. In its most advanced form, this stage is called Photon, a spacecraft bus to support small satellite missions even beyond Earth orbit. It's to this structure that the CAPSTONE satellite is attached, ready to be carried on its way to its lunar destination in near rectilinear halo orbit.
T-minus 5 minutes and 30 seconds on the clock, and from here the launch team will move on to some of the final milestones and checks of Electron, Photon and CAPSTONE before liftoff. The mission will launch from Pad B today at Launch Complex 1, where we have 2 orbital launch pads within our private spaceport dedicated for Electron launches. Now, Rocket Lab launches typically deploy spacecrafts to orbits between 500 and 1,200 kilometers altitude above Earth's surface. But this time, as you'll know, Electron and our upper stage Photon will send the CAPSTONE spacecraft a little bit further than usual, some 1.3 million kilometers further. Around 9 minutes after liftoff, Electron's second stage will separate from Photon, placing the spacecraft bus and its CAPSTONE payload into an initial low Earth orbit of just 165 kilometers. Now, from this initial parking orbit, Photon's Hypercurie engine will perform a series of orbit-raising maneuvers over 5 days to stretch its orbit into a prominent ellipse around Earth. Now, 6 days after launch, Hypercurie will ignite one final time, accelerating Photon to allow it to escape low Earth orbit and set CAPSTONE on a course for the Moon. From there, CAPSTONE's journey to NRHO is expected to take around 4 months, with the CubeSat team at Advanced Space's Mission Operations Center commanding the spacecraft to fire its thrusters to adjust its course accordingly. Now, if we are looking back at the pad camera now, we can see that the rocket's strong back has retracted and has moved into the launch position. This launch platform structure is what holds the umbilical lines, providing power to the rocket, which will fall away as Electron lifts off the pad. You can see Electron's icy white stripes on the outside of the rocket there too. Those are because of the super cold liquid oxygen propellant on the inside of the rocket, which freezes water on the outside, causing it to form those distinctive icy areas along the rocket's black carbon composite body. Now, our last weather update also confirmed that the wind speed at T0 is expected to be good for launch, further minimizing the weather risk to today's mission. Now, as we get closer to the countdown, it is worth pointing out what kind of views to expect from launch today. As always, we'll be bringing you the live views you see on your screen from various cameras at the pad and at range control. However, for this mission, we won't have the typical onboard vehicle cameras you might be familiar with for Electron launches, and that is because this mission has extensive telemetry requirements. So to reduce the load on systems and operators, we've streamlined the mission down to essential systems only. Now, while we won't have those live vehicle feeds to show you, we will be broadcasting mission data and animations so you can keep up with the launch progress throughout the ascent. And now we are coming up to a critical juncture in the lead up to launch, the switch to the countdown auto sequence. The team are tracking no issues with the launch vehicle. CAPSTONE and Photon remain healthy, and the weather is looking good. So at T-minus 2 minutes, very shortly, that autonomous flight computer on Electron will take over the launch countdown, followed by the call that LOX loading is complete on Electron. Then at T-minus 1 minute, we can expect confirmation that the vehicle's first and second stages are pressurized for launch. So, followed by that will be the iconic final countdown to liftoff at T-minus 10 seconds and engine ignition at T-minus 3 seconds. We'll hand over now to mission control and listen into those calls to launch.
Launch vehicle is fully on internal power. Lunar Photon is on internal power.
LOX load complete. LOX system in recirculation. All helium anti-gathering disabled.
Stage 1 and Stage 2 at rest.
High flow engine purge enabled. Water deluge activated.
T-minus 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, lift off.
HVB discharge now.
Stage 1 propulsion is nominal.
Entering burnout detect mode.
Crank shifter on 1.
At T+1 minute and Electron is in the air and onward to the moon for the CAPSTONE mission. That rocket is soaring through this nighttime sky, now past 14 kilometers in altitude in these past few moments. Now things look to be continuing nominally, which means that shortly Electron will come up against max Q, or maximum dynamic pressure. Now this is the moment when Electron will experience its most amount of mechanical stress as it travels through the atmosphere. And I can confirm from mission control that we have had max Q confirmed, so that was a successful pass through that milestone, and Electron is onward to low Earth orbit. So propulsion appears nominal on that first stage, and the Photon lunar upper stage and CAPSTONE spacecraft remain healthy inside the rocket's fairing. We are coming up soon on 3 events in the launch timeline that will occur in very short succession. So soon, the 9 Rutherford engines powering Electron right now will diminish their power and then shut off completely. That command is signaled by the rocket's flight computer and then called across mission control comms as MECO, or main engine cutoff. Now, once that action is complete, Electron will separate its first and second stages. The main booster will continue to slow and remain behind while the second stage carries on with the mission with the ignition of its single Rutherford engine. And we have had MECO confirmed, and will be coming up soon on the fairing separation for the mission. So just to confirm from mission control comms, we have had MECO and second stage separation, and it's carrying on now, as you can see in that animation. So soon we will be coming up to the fairing separation of this mission. That is the jettison of the fairing halves, or the rocket's nose cone that sits on top of the second stage. So now that Electron is well past the Kármán line, we don't need that fairing. It served its purpose to protect the payload and the Photon upper stage during the launch through Earth's atmosphere. So again, that fairing will separate shortly in preparation for the final stage separation between the second stage and Photon. So there we go. We heard it on comms. We have had fairing separation on that second stage. And so there's confirmation that mission is continuing as it should, with Capstone and the Photon Lunar upper stage now exposed to space and no longer needing that protection through Earth's atmosphere. Now, it's very exciting to see this mission up and in the air. And if you have just joined us, we have had a great start to today's journey to the moon. We have successfully cleared the pad at Launch Complex 1 just a few moments ago, and we are now well on our way to space, having completed that first successful pass through Max Q, main engine cutoff, stage separation, and fairing jettison to reach this point now in the mission. Now, Electron's second stage remains attached to the Photon Lunar upper stage carrying Capstone, providing it with that assist to the mission's parking orbit at 165 kilometers above Earth. The rocket's second stage is moving along nicely on its continued ascent, now traveling at a very fast speed of more than 9,000 kilometers an hour. Soon, the second stage on the Electron rocket, which is powered by our vacuum-optimized Rutherford engine, soon the batteries on that engine will need to be swapped out. Now, this is a unique aspect of our 3D printed engines because it's not many engines that are powered by batteries in the first place. In fact, the Rutherford became the first rocket engine in the world to reach space using an electric pump feed cycle when it was first launched all those years ago. Now, how it works is that we keep the engine firing all the way to orbit with the batteries that are powering that engine. But like all batteries do, these ones get depleted of power and we'll need to swap them out with a new set to keep the system running. We call that a battery hot swap, and that moment is coming up shortly. We will hopefully hear that on mission control comms.
Stage 2 is starting to throttle down. Stage 2 guidance remains nominal, 200 seconds remaining.
If we take a look at the graphics on the right-hand side of our screen, we can see the measurements for the propellant on Electron. So on your left, you have the kerosene propellant and the level of the tanks that it is now at. So we're at 45% and counting, sitting at a nice and warm 8 degrees in temperature. And that is very warm compared to the liquid oxygen temperature, our other propellant. So that is sitting at a nice and chilly minus 178 degrees with 40% or so propellant left.
Hot swap.
And there we have the call
Stage
that
2
battery
propulsion
hot
is
swap
holding
on the
nominal.
second stage was successful. Now, next we should expect to hear one of our operators in mission control call out that Electron is orbital, indicating that the rocket is in the right place ahead of stage separation. So SECO, the acronym for Second Engine Cutoff, and the subsequent stage separation follow relatively the same procedure as main engine cutoff, where the Rutherford engine on the second stage will shut off ahead of the final separation of the vehicle between the second stage and the Photon Lunar upper stage. There will be a bit of a gap between that final separation and the first hypercurie burn, as this stage separation places the Photon Lunar upper stage in an elliptical orbit of Earth first. Now, a reminder that 165 low Earth orbit is just the first orbital phase for this Capstone mission, with Photon and Capstone's orbit continuously raised higher and higher over the next few days with a series of engine burns on the upper stage. I'll go into more detail about Photon's phasing orbits and Capstone's path to the moon shortly, once Electron has completed SECO and stage separation. Let's listen into mission control comms.
Entering burnout detect mode.
So a quick check on the speed and altitude of this mission. We are traveling at more than 23,000 kilometers an hour. And while on the right you can see the altitude is at 175 kilometers, what goes up must come down, and we will lower ourselves into that 165 kilometer parking orbit very soon.
Seeker confirmed.
So with the Rutherford engine cooling down, that tells us that second engine cutoff was successful on Electron's second stage. And the Photon lunar upper stage has now departed into its low Earth orbit with the moon-bound CAPSTONE spacecraft on board. Now, as a reminder from here, Photon is in charge of the mission. With its relightable hypercurie engine, Photon will begin maneuvering into a parking orbit just above substantial atmospheric drag, but below the Van Allen radiation belts. It is the perfect, stable platform from which to prepare for lunar departure. Now, once Photon is in the correct orbital alignment, the hypercurie engine will ignite again, performing a burn to lift the highest point of Photon's orbit, the apogee. Now, as it gains altitude and also loses velocity, and so what goes up comes back down as Earth's gravity pulls it back towards the planet. When it reaches the lowest point, or perigee, once again Photon's hypercurie engine ignites to increase velocity and raise its apogee higher. So if you've ever been on a swing set, swung to the top, came back down, and then kicked your legs out to throw your weight forward to reach even higher on the next swing, then you've followed similar principles to what our Photon upper stage will be doing in space. Now, as these phasing orbits get bigger, they take longer to complete. The first will only take around 90 minutes, while the last one will take around 15 hours. Then on the final phasing pass, Photon will ignite hypercurie for a precision translunar injection burn, accelerating the upper stage and CAPSTONE to a top speed of nearly 11 kilometers per second, fast enough to break free of low Earth orbit on its way to the moon. The speed Photon is traveling at this point will shoot it well past the moon's orbit and to the edge of the Earth-Moon system on a transfer orbit. Lined up with the sun and using its gravitational pull to shape Photon's orbit to match speed with the moon, CAPSTONE will then be deployed and carry on the mission solo. And so with those first few hypercurie burns scheduled in the coming hours, I'm going to send it back to Daryl and the team at the Kennedy Space Center. Daryl, I know you weren't here in person, but how was that for you guys over at KSC? My heart is still pounding. I know our team is thrilled at the successful first phase of this mission.
Oh, absolutely, Muriel. Wish I could have been there to watch it with you. And boy, what a beautiful picture from here. And congratulations so far on the success of the launch. Obviously, a lot more steps to go before CAPSTONE gets into its orbit, but looking good so far with a great beginning. Quick note on this rocket right behind me, the Space Launch System, NASA's Mega Moon rocket. It completed its wet dress rehearsal. It will be returning to the vehicle assembly building in just a matter of days. It's going back on Friday. Repaired to the hydrogen leak will be made, and then the next time it rolls back out to the pad right there, it will be ready to go to the moon. And what a beautiful shot that we see there. We are at daybreak here on the east coast of Florida. 5:59 is when first light arrived, and we've got some beautiful pictures there of our moon rocket. And now let's go back down to New Zealand, and joining us now is Bradley Smith, the Director of Launch Services at NASA's Kennedy Space Center. He's with the launch team in New Zealand. And I want to ask you, Bradley, first of all, you're a half world away, and there's a little bit of a small delay between us, but I want to ask you, how did the launch go from your perspective?
Oh, I am definitely half a world away. I landed in Auckland, and my first foray into New Zealand soil was a lost bag, so I had to go buy a new suit as soon as I landed. But yeah, I mean, the launch was absolutely fantastic. I mean, this has been, for me, 8 years in the making. You know, all the way back to 2014 when we put our trust in Rocket Lab with our initial VCLS Demo 1 award, contract award, right? And here we are. You know, that was a payload to go launch university CubeSats, and now here we are, not even a decade later, and this incredible team has just sent CAPSTONE on a ballistic trajectory to the lunar orbit, right? I mean, it's amazing how far Pete Beck and his company have come in the last 10 years, and we couldn't be prouder.
And you've been there on the journey most recently. Did you ever imagine, got to ask you, did you ever imagine that you would launch a mission to the moon on a 59-foot tall rocket?
I did not. And for on the order of $30 million, right? Between the payload and the launch service itself. It just goes to show the direction that NASA's going, right? Embracing this truly commercial approach to enable science and discovery for the agency.
So what's next for launch services?
Yeah, so for LSP, we've got, well, you know, it's as soon as I say we have a certain number of launches, those launches will immediately slip to the right? So we have somewhere in between 3 to 5 launches coming up. We have 2 more venture class launch service class launches, both with providers that NASA has not flown with before. One with Relativity and also one with Firefly. Those will one launch from the Cape and one launch from Vandenberg Air Force Base. And then we have 2 end-to-end missions coming up as well from the West Coast. One is the JPSS-2 mission for our NOAA partners, Polar Earth Observation Satellite. And then we also have SWAT, which is a oceanography payload that's done jointly with CNES. So that's what's next for LSP programmatically. Of course, we continue to support our sister programs, Commercial Crew and Commercial Cargo, doing the launch vehicle work for those payloads as well.
Looking forward to those.
Crew.
Yeah, absolutely. Looking forward to those missions, Bradley. And thank you for your time. And sorry about the rough start in New Zealand, but the new suit looks good on you. But that launch looks even better.
Absolutely. I appreciate it.
All right. Thank you, Bradley. And that concludes our live coverage of the launch of CAPSTONE spacecraft. Over the next 6 days, Photon's engines will periodically ignite, and they will basically accelerate CAPSTONE beyond low Earth orbit and send it on a ballistic lunar transfer trajectory to the moon. If you'd like updates on its progress and how it's performing, there are 2 ways you can do it. You can follow us on Twitter. We're going to pull up a graphic here, @NASA Technology, or you can click on a QR code that we have. We're going to pop that up on the screen. There it is. That will take you to our CAPSTONE blog, where you can also find NASA's Eyes on the Solar System. This is an interactive real-time 3D data visualization where you can virtually ride along with the CubeSat. Pretty cool. We'll have that ready in about a week. And while you're capturing that QR code, I want to do one thing. I want to boop this rocket. Boop. Always wanted to do that. A special thank you to all of our guests on the show, as well as NASA's Space Technology Mission Directorate, also to Rocket Lab for partnering with us on this launch broadcast. I'm Daryl Nail signing off from the Kennedy Space Center with the Space Launch System behind me at daybreak. For Rocket Lab's Muriel Baker and everyone here at NASA, thank you for watching. We leave you now with a replay of the CAPSTONE launch from New Zealand and remind you to keep looking up.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Confirm liftoff.